Today's question comes to us from 2022 and it's the higher paper 1 question 3. And again, we're continuing our look at structure and bonding in anticipation of paper 1. And here we're looking specifically at diamond and other allotropes of carbon. So it says here to describe the structure and bonding of diamond. Now, diamond is an allotrope of carbon. So that means that it is going to go covalent bonding, which is what non-metals do. And actually, if we look at this structure, if I hone in on this one, and they're very helpfully put the extra lines in, you can see that each carbon is bonded to 4 atoms, which is what we'd expect actually, because remember, carbon's in group 4. Describe doesn't mean we need to explain, but we've just done that a little bit verbally just to help us with our revision. So the first thing to note is it is a giant structure, and this is because this can go on forever. There are strong covalent bonds, and think about how this is different to simple molecules where we have those weak intermolecular forces. And finally, that each carbon atom is bonded to 4 others. That's enough for 3 marks, and if anything, I was stretching it out. Next thing is explain why diamond has a very high melting point. So this is just taking what we've said before, but just that one step further. So similar to those questions that we've answered before, when we're thinking about the structure, we've got to think about the bonding. And when we do covalent bonding, we have several options, but the 2 main ones is we have simple molecules, and simple molecules like, let's say, chlorine, we have our molecules with our strong covalent bonds, but we have weak intermolecular forces. These are easy to break, and that's why it has a low melting point and boiling point. But diamond does not. Diamond has a very high melting point, and that's because diamond is, as we just discussed up there, a giant covalent structure. Because this goes on forever, you'll notice that there's no weak intermolecular forces. What this means is if I want to break apart the carbon atoms, I have to overcome those strong covalent bonds. That's tough, so that's why we've got a high melting point. Let's put it together into the answer. Diamond is a giant covalent structure with strong covalent bonds. These bonds are strong and therefore take a lot of energy to break. And to break them is what we need to do to melt them. And therefore we've got a high melting point and boiling point. The next part of the question takes us on to another allotrope of carbon. Just as a side note, remember, allotrope is different structures of the same element. So figure 2 represents the molecule C70, slightly different to the C60 that maybe might ring a bell. What is the name of this type of molecule? So it's a fullerene, okay? But let's think about what the others are. Graphene is a single hexagonal sheet of carbon. So graphite is where you have multiple of these layers. Graphene is a single layer. Nanotubes are kind of similar to fullerenes, where we get this sheet kind of fold up into that. And a polymer is where we usually think about them as alkenes, but we also have condensation polymers, where we get carbon chains kind of formed, a long carbon chain. So fullerene is like a ball. Molecules such as C70 can be used in medicine to move drugs around the body. Suggest one reason why C70 is suitable for this use. Well, if we look at here, inside there is empty space, just like in the middle of my head. If I've got that empty space in there, I can chuck a drug in there and that can carry it around the body. I think we sometimes think about this as like, oh, it's got air in it or something, especially because we compare these to footballs. But remember, this is on the molecular level. There's no atoms in there, there's literally nothing. Now, there are a few other reasons if we want to get more complete. And if we're giving someone something to do with medicine, it's important that it's non-toxic. And this is just made of carbon. And even though you'd be a bit weird cracking into a little lump of charcoal for dinner, it's not going to kill you. Okay? In fact, activated charcoal is a remedy for certain poisons because it's very absorbent. It's very unreactive. It's quite content in its shape, and therefore it's going to be work okay as a drug carrier. Next one says, calculate the number of C70 molecules that can be made from 1 mole of carbon atoms. The Avogadro constant is 6.02 times 10 to the 23 per mole. If you remember, a mole is simply a big number of atoms. It's specifically 6.02 times 10 to the 23. And the reason that we use this number and this number is useful is because if I have 1 mole of atoms, then it would weigh its RFM, its relative formula mass, in grams. So if I have 1 mole of carbon, 12 atoms, it would weigh 12 grams. Now that's not relevant to here, but I just wanted to think about what actually is the point of a mole and why do we end up with this weird number. It's because we worked kind of backwards. So how many C70 molecules can be made? So if we've got this number of carbon atoms, C70 means that I'm going to use 70 per molecule. So if I simply divide it by 70, that's going to give us our answer. After technical difficulties of looking for my phone to use a calculator and then realizing that this is recording this, let's put that into the calculator. And when we do that, we get 8.6 times 10 to the 21, and that is our answer. And this is a really good time to mention the fact that, especially with standard form, things can go wrong, but as long as you've got your work in there, you would get at that point 2 marks, okay? So just remember that that is a really good kind of safety net. So good little look back into the properties of the allotropes of carbon and a little bit of quantitative maths with moles at the end.